All right, let's jump right into this explainer. Today, we are unpacking a really fascinating April 2026 paper by independent researcher Mohammed Ben Ammar Trady. If you've ever found yourself wondering how we can actually mathematically trust complex artificial intelligence to behave predictably, this is exactly the architecture you need to know about. It's essentially a blueprint for keeping AI systems perfectly stable, and we're going to follow Trady's work all the way from the pure mathematical theory down to the rigorous empirical validation. Here's our roadmap for the breakdown. We'll start by meeting the AAO framework, then we'll dive into understanding Lipschitz bounds, compare index versus multi-set models, check out the empirical calibration protocol, weigh empirical against conservative certification, and wrap up by looking at how this models dynamical systems.
Section 1. Meet the AAO frameworks.
So we all know the fundamental issue here, right? Modern AI, particularly in scientific machine learning, often operates as an unpredictable black box. You feed data in, something massively complex happens, and it spits out an answer. Well, Triety introduces the Aggregation-Attention Operator, or AAO. Now, it's really important to note that he isn't claiming to have invented some radically new neural layer that replaces everything else. Instead, the AAO acts as a universal mathematical language. It takes all these diverse existing mechanisms, like attention layers or graph message passing, and structures them into a single unified template where things like well-posedness and stability can actually be mathematically proven. You can think of the AAO kind of like stations on a highly controlled factory assembly line. First up, we have local pre-processing, where the individual data points are initially transformed. Next is contextual weighting. This is where the model looks around and decides how important each part is based on its surroundings. Then we hit aggregation, the station that combines everything using a strict interaction rule. And finally, the final readout maps that combined state to an output. By modularizing the network this way, we can isolate, test, and guarantee the stability of every single step.
Section 2. Understanding Lipschitz bounds.
Okay, but what actually keeps this assembly line from breaking down if there's a tiny glitch in the raw data? How do we guarantee that a minor error doesn't snowball? That's where our stability constants come into play. We're talking about Lipschitz stability bounds. In plain language, these act as the mathematical speed limits, or the shock absorbers, for our AI. Schreitz's paper explicitly derives these constants, completely separating the sensitivity of the local features from the aggregation mechanism to ensure the system remains entirely predictable. And what's brilliant about this is how it formalizes the transformation of local maps into global estimates. By identifying the local constants, say how one specific context weight behaves, the AAO framework mathematically proves that this local regularity translates directly into global robustness. So you're not just crossing your fingers and hoping the whole network is safe. You have a rigorous, certified guarantee.
Section 3. Indexed versus multi-set models.
Of course, data doesn't always come down the assembly line in the exact same way. The framework has to handle two completely different setups. On one hand, we have indexed aggregation. This handles strictly ordered data, like time series, where the sequence matters absolutely. On the other hand, we have permutation invariant multisets for unordered data. Think point clouds. This is basically a chaotic sorting bin, where the exact order doesn't matter. To mathematically control that chaos, Triety uses an unnormalized W1 type matching cost. It's essentially a rigorous way to calculate the minimum effort required to match those jumbled items together, ensuring our stability guarantees still hold firm. Section 4. Empirical Calibration Protocol. Now, you might be thinking, okay, theoretical speed limits are great on a chalkboard, but how do we know they work in the computer? Well, the paper outlines a super rigorous Monte Carlo testing protocol to bridge that gap. Step 1 applies spectral constraints, which act as a strict volume dial to control operator norms. Step 2 brings in Jacobian-based sensitivity estimation, kind of like testing the sensitivity of every individual knob on the machine. And Step 3 hits it with Monte Carlo perturbation tests, where we basically throw random variations at the model to stress test it. This ensures our constants are verifiable, operational facts. Section 5. Empirical versus conservative certification. Running those stress tests brings up a massive question for AI certification. Do we want bounds based strictly on how the model behaves with standard data, or do we want absolute worst-case structural safety? Notice the difference in these plots. On the left side, with empirical calibration, you see a tight cloud of data just below the red threshold line. It's sharp, and it's adapted to what the system typically sees. But over on the right, the conservative certification shifts that data cloud way down. It relies on structural activation bounds and spectral norm limits, making it a much looser but ultra-safe architecture-aware estimate. And if we look at the histogram showing the ratio of observed variations to theoretical bounds, the success of both methods is undeniable. See that red dashed line marking the theoretical safety threshold of 1? Both the empirical data and the ultra-safe conservative data are strictly below it. The math absolutely holds up in both regimes. We are talking 0 empirical violations. Section 6, Modeling Dynamical Systems. To prove this isn't just theory, the AAO was deployed as a robust propagator to predict complex, one-dimensional reaction-diffusion dynamical systems. Just look at the rapid convergence here. The training loss plummets immediately, and then it forms a completely stable, overlapping plateau with the calibration loss. There's no gap, no overfitting. This proves the architecture can serve as a highly accurate, one-step AI surrogate for complex physics while remaining completely certifiable.
So what is the ultimate takeaway here? Schraby has managed to convert incredibly dense mathematical proofs into practical, certifiable speed limits for machine learning. In high-stakes environments like medical AI or autonomous driving, we absolutely cannot afford to let small data errors cascade into catastrophic failures. By giving us a unified language for both ordered and unordered data, and by balancing tight empirical performance with conservative certification, the AAO gives us a framework we can actually trust.
We are officially entering an era where AI cannot just be highly accurate, it has to be provably safe. I hope this explainer leaves you thinking about how mathematically certified architectures, like the AAO framework, will become the absolute foundation of every high-stakes AI system we build tomorrow. Thanks for diving into the math with me today.